Hello. This is my submission for homework 4. Just checking out the project. We're asked to do problem 3 and 8 from each of these two different files. For problem 3, I did it on paper. And yeah, for all sets, we're asked to use these x's, which I'd call images here because that's what we called it in class. We're also asked to draw the vectors and find the y's in corresponding matrix. So the first one we're asked to find a representation using these x's of theta. So we have our x's here. We have our y's that we found. We have the individualized matrix representations of, for instance, an x projection and a y projection. And then we combined these, as you can see here, that, there, to get our R, which is our representative matrix of this theta rotation angle in the counterclockwise direction. The next one, we are given these two equations, y1 equals 0x1 plus 1x2, y2 equals 1x1 plus 0x2. As you can see, 0x2, 0x1. Well, let me just start from the beginning. Okay, so we have 0x1 plus 1x2, so 0x1 plus 1x2, 1x1 plus 0x2. We are asked to use these x's, so there's our x for this one, there's our x for this one, and then we get these corresponding y values if you just multiply these in a calculator. And this is a reflection over the x over the line y equals x. So basically this line here goes there, and this line that starts here ends here because they flip over this 45-degree line. Next one, this one you can tell is going to be projection onto an axis because 0x1 plus 0x2, and then we have 0x1 plus 1x2, so it looks like it's going to be projected on the y-axis. We try our x here, that represents our x vector. We yield 0, 0, so this arrow is just going to go to 0, 0. It's non-existent. Then we try our y vector representation, our y-axis representation. We see that it's the exact same as what we were given in the x here. So it's just projection on the y-axis. You can see that here, and you can see that one here, and you can see, got all the graphs. Here, y1 equals x1, y2 equals x2. This is very clear to me that it's going to be just an unchanged one, both the vectors being unchanged. And when you multiply it out, you can see the x's is the same as the y. X is the same as the y. The matrix doesn't really affect it. And that's what a graph representation would look like. Vectors don't change. Here, everything is halved. So we're kind of taking like an average, if you will. So right here, you can see there and there. If you add those two and divide it by 2, you get here, right? So it's kind of like the average in between here. But let's go through the math. You got your formula y equals mx. We've been writing on all of them. Got both of your x's. This one for the x-axis, this one for the y. Same thing. And same m in both of them. These still come out the same. You get your halves. So this projects both of these onto the line y equals x. And then on M4 linear system, problem 8.1 I did here. The largest number, the absolute value of the largest number that these are, is on the diagonal for all. So you can see 2, 2, 2 is larger than, well, 2 is the biggest number in this matrix. So, but it's larger than the other ones in the rows of the columns. Okay, so on to my MATLAB code. All right, so now I'm on my MATLAB code. just to prove, or just to show which matrix I used for the part 1 of that problem. It was from this example, and I used this matrix so you can see the 2's in it are the largest on that diagonal. All right, and problem 8. Sorry to did this. We then use naive Gaussian elimination to solve the linear system of this augmented matrix. So you have your augmented matrix right here is M. P is going to be my pivot, and C is going to be my coefficient for this part. So we have our first pivot here, which is this 2 right here. Our first coefficient that we use is this 3, and then our next coefficient will be 3 and 3. I did all these on MATLAB, so as you can see, our coefficients are here, and then we have the corresponding formulas for these coefficients. So this is essentially just saying rho 2 equals rho 2 minus the coefficient over the corresponding coefficient of rho 2 over the pivot, which is the same for everything, times rho 1. And you see that here with rho 3 equals rho 3 minus coefficient over pivot times rho 1. Rho 4 equals rho 4 minus coefficient over pivot times rho 1. Here it just so happens that all these coefficients are the same, but this will change obviously with our next pivot that we make, which will be this 1. Our third pivot will be this 3. So here's our second pivot. Same formula, except same everything as the first. It's just rinse and repeat, except we drop a formula. We drop this because rho 2 now stays the same because it's the pivot row. Because it's the same row that holds the pivot. And third row, since the third row holds the pivot, rows 1, 2, and 3 aren't changed, and only row 4 is in the same formula. Then we make an array for our x's. We have our x4 we solve for because it's the easiest. So it's the only one that's possible without any other x values. So we solve for x4. We use x4 to solve for x3. We use x3 and x4 to solve for x2. And then we use x2, 3, and 4 to solve for x1. Then when you run the code, I'm going to clear it so you can tell. It's like my third time filming this. You get the numbers. Okay. Part 2, we use partial pivoting for Gauss elimination rather than naive. Same matrix. The only thing we add really is just this to each before each pivot. So you can see it here. You can see it before the pivot here. See it before the pivot here. I'll go into depth a little bit on this. So this first value, this just kind of ignores it. The second is this index, and you set it equal to the biggest absolute value. So all these are positives. This absolute value doesn't really matter, but the larger value between row 1 and 2 in column 1, so the larger between the two. If index logically equals 2, then you do the swap that you need to do. And then it's just the same thing. Pivot. Same pivots points as all the others. I didn't use the whole coefficient term here. I just plugged in the direct coefficient rather than making like a C equals. It just takes a little bit extra time doing that. But I've already made it known that I know how to do that, so that's just why I did it here like this. And the same flipping is if you do rows 2 and 3 and column 2 because you go down the diagonal. We don't care about row 1 anymore. We start here. So we do row 2 and row 3. And then the next one we'll do here, column 3. It'll be row 3 and row 4, which you can see here.
find the access way. Same thing, the indexing, the swapping, all of it's the same. Solving for your x's, you go x4, 3, 2, 1. Always go from bottom to top to get it because the bottom has no variables. And the top one is the most. So you got to use the bottom to the top to stair step up pretty much to solve for x1. And let's display it. Same values. And then this third one, we don't use an augmented matrix. We use just the normal matrix we're given. We take the stuff that's equal to, so like it's like 2x1 plus 2x2 plus 3x3 plus 2x4 equals 2. We take all our numbers on the other side of the equal sign, put them in their own matrix, put the other one, or put them in their own vectors essentially. Take the other one, put it in its own matrix, and then we do the backslash. And it gets you that same thing. It's way quicker. And yeah, that's all I have. Thank you.